This is lesson 60 of the Quantum Mechanics, a mini lecture series, operators part 5. So in the previous video, I talked about Hilbert space, and it's really important sometimes to use the matrix representation of an operator to define the important concept of what's called a Hermitian adjoint. Okay. Let me explain. So suppose we have some operator O hat, and it's got the following matrix representation. Okay, some operator O. We can construct a new matrix by taking the complex conjugate of its elements. Okay, in other words, we can take the opposite sign of any imaginary numbers, if there is any, and then we flip the rows with the columns, also known as a transpose. So take complex conjugate, that's your first step. So for example, I becomes minus I. Second step, we take the transpose. In other words, swap rows with columns. So we get this new matrix. Okay, it helps with an example. And this matrix represents a new operator, O hat, with like a dagger symbol. That's called the Hermitian adjoint of O. Let's do an example. Suppose we have the operator O given by this matrix, 1 minus I, 1, I, 0. Now to determine its Hermitian adjoint, we need to take the Hermitian, the complex conjugate of its elements, and then swap rows with columns. Okay, so the first step is this. So therefore, the Hermitian is just swapping, so taking this to become a row and this to become a column. So 1 plus I, 1, and then the minus I goes up here, 0 right there. And in general, this shows also that operator O is not equal to its adjoint, Hermitian adjoint typically. Okay, it's an operator is said to be Hermitian if it satisfies the following relation there. So Hermitian operators, they play the important role of representing the physically observable properties of a quantum system, like position, momentum, energy, etc. So that they play a big role in quantum mechanics. Okay, they represent physical things. Suppose we have some operator now, let's call it U, which satisfies the following relation. We can conclude that the inverse of U is just the same as U. Okay, I is the identity matrix, identity operator. Okay, let's say 1, 0, 0, 1. Okay, it's like multiplying by 1. Okay, so from this relation, we see that U hat and U dagger hat, they're the same. So therefore, the inverse of the matrix is the same as the original matrix. Okay, and the operator here, U, is said to be unitary. Unitary, U for unitary. An example of a matrix is the following, 0, I, 0. That's a unitary operator. If you take the Hermitian adjoint of this, you'll get the following. Okay, if you multiply the two, you find that you get the identity matrix, 1, 0, 0, 1. Okay, in the two-dimensional case. And I'll leave that as an exercise for you to do. But that's the idea of operators, right? You can do a lot of things with them, manipulate them, represent them as matrices, etc., etc.